Good. So, let's take a look at the syllabus. That's the syllabus is this one right in here. Let's see. Okay, we are writing here. Writing here on Wednesday, 1st of April. We're going to start chapter 22, which is electromagnetic induction. We're going to do lab number 3. Just as let's both face it. We're going to have a break next week, spring break. And then we come back on April 13th, okay? And let me put it here. I was asked to extend the deadline of the reports of labs 1 and 2, and I posted notes here about that, an announcement about that. And you may now turn the reports of these 2 labs the day after tomorrow. The day after tomorrow, April 3rd, until 11:59 p.m. Okay. The lab that we're going to do today, the lab 3, we're going to do today will be the report, right? The report for lab 3 we're going to do today will be due at the day of the day of lab 4. And unless I tell you otherwise, the due date of lab 3 is going to be, since we have a holiday, right? A spring break. And on the top of that, soon after the spring break, we are going to have an exam. Then the report for lab number 3, here should be lab number 4, should be on 22nd of April. We'll be doing the day of lab 4, the April 22nd. And by the way, that's spelled out in the syllabus, right? Lab reports are due at the day of the next lab. Unless I tell you otherwise. Go lab 3 due. We don't have enough. Let's see. Lab 3 due. Right in here, let's see. Lab, yeah. Single resistor. Okay, let's start talking about electromagnetic induction. It's a very important phenomenon that was discovered in the mid 1800s. Let's take a look at the historic background of electromagnetic induction. Okay, historic background of electromagnetic induction. Okay, right in here. Electromagnetic induction was discovered by Michael Faraday in 1831, with Joseph Henry independently discovering it around 1830, 1831. Faraday was a British, right? Back in 1831, British was the superpower of the time. Here you go, Michael Faraday, an English English chemist and physicist. But it was also co-discovered by Joseph Henry as well. Let's take a look at Joseph Henry. Here, this is an American physicist. So the Americans was already flexing their muscles at the time, right? In the mid 1800s. So they just people would say the independent discovery. That's they independently discovered. But we credit more Michael Faraday for that than Joseph Henry. Okay, and here is the historical milestone that we have been covering in this course. 1820, Hans Christian Ørsted discovered that electric current produces a magnetic field. That's what we just covered, right? And we have that Ampere's law that that mathematically documents how an electric current produces a magnetic field, even though it was Hans Christian Ørsted that discovered that. The law was named after Ampere's. Okay, that was 1820. In 1831, Faraday wrapped 2 coils of wire around an iron ring. When he connected one coil to a battery, a wave of electricity, right, was briefly induced in the other coil. I'm going to explain step by step how this thing happens and how important it is. I mean, by the way, it's very important. Electromagnetic induction is a very important phenomenon that we use at home and to transmit electricity. Faraday, September to October 1831, Faraday demonstrated that moving a bar magnet, see that, in and out of a wire coil produced the current. That's the easiest way of visualizing electromagnetic induction. Even though it appears that those 2 procedures here that was documented look different, they are actually, the principle of them are exactly the same. Okay, exactly the same. Faraday wrapped 2 coils of wire around an iron ring, right? When he connected one coil to a battery, a wave of electricity was briefly induced in the other coil. The setup is different, but the principle behind those 2 setups are exactly the same. Is the principle of electromagnetic induction. In 1832, Joseph Henry independently discovered induction, including self-induction, which occurs when a circuit current changes, causing a spark of voltage upon disconnection. Okay, that's self-induction. He discovered Bose induction, but we credit Joseph Henry because he discovered self-induction. Faraday didn't observe self-induction, didn't discover self-induction, but Faraday did discover the induction. Okay, what's the difference between induction and self-induction? Induction is that when one circuit induces a current in the other circuit. Self-induction is when a single circuit induces a current change in itself. Okay, that's why it's called self-induction. And then we have 1834 Lenz's law. We're going to cover all of that, okay? Formulated a law explaining the direction of the induced current, ensuring compliance with conservation of energy. And then in the mid 1860s to 1870s, James Clerk Maxwell formalized Faraday's work into what we know Maxwell's equations, unifying electricity and magnetism. That was the crown jewel of accomplishment in the electromagnetic theory. It was because of this unification by James Clerk Maxwell that we today have cell phones, we have wireless communication. The mathematical, the theoretical background was spelled out by James Clerk Maxwell. And then later on, people like Tesla and Marconi, they put that in practice after someone else called Hertz. Okay, that's the historical background behind induction, electromagnetic induction. So let's okay, today's chapter 22, electromagnetic induction, a new law of physics. Okay, let's recall what are the laws we have so far. Okay, we talked about the magnetic force in the moving charge and also in a wire carrying current. This law we call Lorentz force law. We thought the first one that we thought was the Gauss law of electricity, right? Here you go. Gauss law of electricity and Coulomb's law, which is a special case of Gauss law of electricity. Let's put that here. Coulomb's law is a special case of this law. Okay. Those are the things that you have to memorize in physics, the laws. Those laws cannot be derived. Why do you have to memorize? You have to memorize those laws because those laws cannot be derived mathematically. They can be obtained only by experimentation. They are independent of any mathematical derivation that we have, okay? So the laws of physics cannot be derived mathematically, comma, they are obtained from experimentation in the lab. That's why you must memorize them. And here one of them, Gauss law of electricity, Gauss law of magnetism. Okay, that is no magnetic monopole in isolation. Let's put this. Unlike electric charge, we have a positive and negative charge. We do not have a positive and negative magnetic charge in isolation. Nobody has ever observed something like that. Some people claim that there are magnetic monopoles in nature, but nobody has ever observed magnetic monopole. And the next one that we just saw was Ampere's law, the one discovered by Ørsted, right? Going back here. Where's Ørsted here? Hans Christian Ørsted, right in here. Why is that? He discovered and someone else gets the credit for the law that he discovered, right? Ampere's got the credit. Ampere's law. Here you go. Here's Hans Christian Ørsted. He's a Danish. He was a Danish chemist and physicist. Okay. And what about why is that? Well, let's see if they have Ampere's here in his biography. Ampere. Okay. Okay. Ørsted's findings steered much research into electrodynamics throughout the scientific community, influencing the French physicist André-Marie Ampere's development of a single mathematical formula. Okay, so the situation was like that. Ørsted did the experiment, observed that a current produces a magnetic field, but then he stopped there. He didn't come up with the theoretical foundations of what he observed. It was Ampere himself who came up with that equation that I presented to you. Okay? So that's why we call that law Ampere's law. But the discovery was by Ørsted. Okay? Single mathematical formula to represent the magnetic forces between current carrying conductors. That is the experiment that he did, that explanation that Ampere did. First, he observed the magnetic force between current carrying conductors. Okay? And then later on, we found out that the electric charge in motion would suffer a magnetic force. Okay, the Ørsted effect brought about a communications revolution due to its application in electric telegraphy, electric telegraph. The possibility of such a telegraph was suggested almost immediately by mathematician Pierre-Simon Laplace. Okay, Laplace is another giant in physics. Okay, and Ampere presented a paper based on Laplace's idea the same year as Ørsted discovery. However, it was almost 2 decades before it became a commercial reality. 20 years, right? To put in practice into a commercial device, to put a scientific discovery into a commercial device. And Ampere's law. And now let's talk about electromagnetic induction, right? What is electromagnetic induction? So I'm going to spell it out in a very simple way what electromagnetic induction is, okay? Up to now, I suggested, right? I implied that the only way to create a current, an electric current, in a circuit, in a wire, right? In a conducting wire, is by connecting this wire to a battery, to a source of electrical energy, to a battery or a source of electric energy. That's what I have suggested. But there is another way. Of creating a current in a circuit without a battery. Okay? This phenomenon is referred as electromagnetic induction. Okay. Referred to as electromagnetic induction. That's what electromagnetic induction is. It's the process of inducing a current in a circuit that is disconnected from a battery, a closed circuit that's not connected to a battery. Okay, in short, electromagnetic induction is the process of inducing, okay, or creating a current in a circuit. Let's put it closed circuit for now. Closed circuit without a battery. Without a battery. And let me just illustrate here for you. Okay, so consider yourself, here you go, a current loop, no battery in the circuit. If you don't do anything else, there will be no current flowing in this circuit. But if you do something else other than inserting a battery in the circuit, you may induce a current. This current is called the induced current. You generate a current in a circuit without a battery. And how that is done, right? Let me show you a video so you can appreciate in real life how this thing is done. The best way to do it is to get a coil. A coil, or let's say there's another name, right? A coil or here you go, something like that, okay? Which is a coil, right? That's what you have here, is a coil with several loops around. The best way, okay? You can do that with just a single loop, but this device becomes more sensitive to induced current when you have several coils in a single device. And that's what we have right in here.
These are neodymium magnets.
Here you go.
Neodymium magnets.
We're going to talk about the neodymium magnets very soon.
In this
here you go. Here you go. Here's a coil, right, with several loops. Can you picture that? You know, you can wrap around all those wires around your hand and form this coil with several loops there inside. The more loops you have here, the more current you can generate by electromagnetic induction. And what we have right in here is just your multimeter. It's measuring the amount of current that's going to flow through this device, okay? And then what do you need? The easiest way of demonstrating it is with a magnet. That's what she said is a neodymium magnet, right? A bunch of neodymium.
These are neodymium magnets.
Neodymium magnets. Why neodymium magnets? Okay, neodymium magnets because they are very strong. You can buy them. They're mass manufactured out there. You can see that's one neodymium magnet. That's another neodymium magnet. All of them stuck into each other. And when you pile them just like that, all those neodymium magnets act like a single magnet that's much stronger than a single neodymium. Okay.
Neodymium magnets have very strong magnetic field. In this video, we will use these.
Do you see what happened? She just approached the neodymium magnet, and then the needle of your ammeter moved, right? Indicating that there was a current flowing through the coil. Let's take a look again. Here you go.
In this video,
see that?
We will use these magnets to produce electricity, a phenomenon known as electromagnetic induction.
Okay, you can even, isn't that nice, Figo? You can even turn on your LEDs by doing something like that without a battery. Okay, here what they did, they connected LEDs to this loop, to this current loop. And by rotating the neodymium magnet, what she's doing, she's changing the magnetic field. If the neodymium magnet is at rest, you wouldn't be able to generate a current, to induce a current in the circuit. Okay?
Magnetic induction. First, we need to identify the poles of the neodymium magnets. For this, we will use a magnetic
She's identifying the pole of the
Now,
neodymium magnet so he can predict the direction of the current.
We know that like poles repel and unlike
But
poles
that's the
attract.
that's the basic idea of electromagnetic induction. By changing the magnetic field in a coil, okay, which was exactly what she did here at the beginning, okay? She's changing the magnetic field that this coil is subjected to by approaching and receding the neodymium magnet.
In this video, we will use these magnets to produce electricity.
When the neodymium magnet is at rest, right? No current is induced. Let me show you it again. There are lots of
to produce electricity.
Here you go. See, the neodymium magnet is momentarily at rest. So the current induced is very small.
Electricity.
Okay, here you go. Current is zero, right? You have to move the neodymium magnet or any magnet, not just the neodymium magnet, but any magnet to induce
a phenomenon.
This electric current. And when she withdraws the neodymium magnet, now the magnetic field here presents by subjecting this coil decreases in time, right? And the current just shut out, increases so much that the needle is no longer here in the scale, right?
Known as
here you go.
Electromagnetic
and that's another way. You can approach the neodymium, the magnet, you can approach and recede the magnet, and you're going to induce a current. Or you can do what she's doing here, just rotate the magnet inside the coil. And to prove that she's generating a current, she connected those two LEDs to this coil, and the LEDs keep on blinking back and forth, right?
First, we need.
So that's the simplest way of understanding the electromagnetic induction. Let's see this experiment again. It's just a repetition of what I said, okay? It's a repetition of what I said. We get the coil.
We take a coil off.
Here you go, the coil. There are a bunch of turns around this coil. Why we have a bunch of turns? We have a bunch of turns to amplify the induced current. You can do just with a single turn, but it's going to be difficult to see the current induced in the coil.
An insulated copper enameled wire having 500 turns.
500 turns.
You connect the end of the copper coil.
Then you connect it to a galvanometer, which is nothing but an ammeter, a device that measures current or even voltage. A voltmeter would do the job as well.
Galvanometer.
Now you connect
can detect the presence of electric current in
the leads of your coil to this galvanometer.
The circuit. It also indicates the direction of electric current in the circuit. Galvanometer shows deflection.
And then you're going to see the deflection,
right,
just like you saw before.
Current is detected by the device. Bring the north pole of the neodymium magnet
approach
to observe
north.
Deflection.
See?
Pay attention to the direction.
Pay attention to the direction. When we insert the magnet in the north direction, the galvanometer needle is deflected to the right. You come to rest with the magnet, and there is no induced current whatsoever. Now she's going to withdraw the magnet. Look what's going to happen to the needle.
Of deflection.
Here you go. The needle is deflected to the left. Okay, let's play it again. Here you go. Let's play it again. You're going to insert the magnet into the coil. When you insert, the magnetic field increases, the needle deflects to the right.
When electric current is detected by the device. Bring the north pole of the neodymium magnet close to the coil.
Here you go. The needle deflects to the right.
Deflection. Pay attention.
When we withdraw the magnetic field in the coil is going to decrease,
attention to the direction of
and the needle deflection is to the left.
In our setup,
needle deflection to the right and to the left means what? Means the direction of the current. Okay? One current is flowing in the clockwise direction, the other core current is flowing in the counterclockwise direction. That's what the positive or negative deflection means. Let's write that down. Okay? Ways to induce a current in a circuit. Okay? Different ways to induce a current in a circuit, in a closed circuit. And let me also give you a link for this video, YouTube video. And then you can search for other videos as well. I like this one, YouTube video explaining electromagnetic induction. Okay. Different ways to induce a current in a closed circuit. One, a closed circuit use a magnetic bar approach, right? Approach and receive a magnetic bar to and from the circuit. Okay. So what's happening here? What's happening here? When you approach the magnetic bar to the towards the circuit, right? Towards the circuit, comma, the magnetic field felt by the bar, by the circuit, not by the bar, by the circuit, increases in time. Okay, instead of approaching, let's put here varying by varying the magnetic field that a circuit is subjected to. One way to do that is by approaching. One way to do that is to approach and receive. Approach and receive the magnetic bar to and from the circuit. It is better that this circuit has more than one turn, so it can amplify the induced current. You can do with a single turn, yes, but it's better that you do is more than one turn. So each additional turn amplify the induced current. When you approach the magnetic bar towards the circuit, increases in time. When you receive the magnetic bar from the circuit, comma, the magnetic field decrease with time. Okay. When you receive them from the circuit towards the circuit, when you receive them from the circuit, the magnetic field decreases in time. In both cases, you have a magnetic field that changes with time. Okay, in both cases, you have a magnetic field that changes with time. Okay. When you approach the magnetic field, magnetic bar towards the circuit, comma, the current flows in one direction. Okay. When you receive the magnetic bar, from the circuit, the current flows in the other direction. In the other direction. That's how it goes. And that's exactly what you saw. Okay. Let's see. Let me organize that, The way to induce a current in a closed circuit is by varying the magnetic field that the circuit is subject to. And now we have different ways. One way to do that is to approach and receive the magnetic bar to and from the circuit. Okay. And here in my illustration, right? Here you go. We have this induced current, and this current is being induced because we have a magnetic field. Okay. That's the direction, right? Of the induced current is rotating. In this case, is in the clockwise direction, right? And then I put here this vector into the board to illustrate the fact that the current is in the clockwise direction. Okay, so here you go. So if you have a magnetic field that's varying in time, that's what those black arrows is all about. Okay, it will induce a current in the circuit. Let's see if I'm going to reorganize this thing. I don't like the way it is. Okay, we have here you go, this one here. Okay, so now we have, if you have a magnetic, let me erase this one for now. Let me erase this one for now. Subject a magnetic field, subject this loop to a magnetic field, and what else you do? And you vary the magnetic field in time. Let me erase this one. When you vary a magnetic field in time, you are going to induce a current. And let's see, I'm going to do like that. You're going to induce a current. The direction of the current depends on the direction of the magnetic field plus the amount of change, how the magnetic field is changing. Okay, and there is a very simple way of determining the direction of the current by using Lenz's law. Okay, that's the illustration that you have to keep in mind. Here you go. Current loop, no battery in the circuit. You subject the current loop to a magnetic field, and on the top of that, you change the magnetic field in time. When you change the magnetic field in time, when you vary the magnetic field in this loop in time, an external magnetic field, you induce a current in the circuit without a battery. The direction of the current is going to depend whether is going to depend on the direction of the magnetic field and whether the magnetic field is increasing or decreasing. Okay, that we can write that down. Okay, the direction of the induced current in the wire will depend on two things. Okay, the direction of the magnetic field and whether the magnetic field is decreasing or increasing. Like that, okay? One, the direction of the magnetic field, and two, whether the magnetic field is increasing or decreasing. If the magnetic field doesn't change, if the magnetic field remains constant, comma, no current is induced in the closed loop circuit. Okay, and say, here you go, just one way of changing the magnetic field, right? What's another way of changing the magnetic field? What's another way? Another way to change the magnetic field, comma, is by placing a second circuit next to the first one. This second circuit would have a battery, okay? You turn on the second circuit and turn it off, okay? When you turn on the second circuit, comma, a current builds up. A current builds up on the circuit. And this current produces a magnetic field that changes in time. Do you remember what I told you? You know, remember that B, right? B is a function of the, here you go, is a function of the current. It's actually a, let's see, it's a constant times the current, right? As the current increases, the magnetic field is going to increase as well when you turn on. Okay, that's what's happening. So that's another way of changing the magnetic field that a circuit is subjected to. This C that you see here is a constant, okay? When you turn on, right? When you turn on the second circuit, a current builds up on the circuit, and this current produces a magnetic field that changes in time. In this case, magnetic field increases. Magnetic field increases, right? When you, after some time, this current stabilizes, right? It stabilizes. Stabilizes. And so there's the magnetic field. And no current is induced in the first circuit. Now, next, when you turn off the second circuit, its current decreases as well as its magnetic field. And now we have the same situation, right? In which the current is also a function of time, but the magnetic field now decreases. That's another way of inducing a current. Can you picture that? Let's see if she has a video on that, right? Let's see here. Let's see. Yeah, this she doesn't have. Okay. Another way to induce a current, right? Another way to induce a current in the first circuit is by rotating the magnet nearby the circuit. And here you go. And she did it. You saw that, right? Let's take a look here. This one right here.
Neodymium magnets are rotated in the coil.
LEDs
glow indicate that there must be some current induced in the coil by the magnets.
The LED is indicating that there is a current induced in the coil. The current is flowing one way and then it's flowing the other way just by rotating this magnet. When the current is flowing one way, this LED here turns on. When the current flows in the other way, this LED turns off and the other one turns on. Okay? That's one way. That's another way. There's a fourth way that's similar to the third way. Okay? Another way to induce a current in the first circuit is by rotating the magnetic bar nearby the circuit. A fourth way to induce a current in the first circuit is by rotating the circuit, okay, nearby a magnetic bar. Okay. Here what we have, mechanical energy is used to create electrical energy, to induce, right? Let's put it, to induce electrical energy. Okay. Here in this case, electrical energy from one circuit is used to induce electrical energy in another circuit. Electrical energy from the second circuit is used to induce electrical energy in the first circuit. Here again, we have the same situation. We have mechanical energy because we are rotating, right, the device. Mechanical energy is used to induce electrical energy. And here we have the same situation. Mechanical energy is, oh gosh, mechanical energy, let's see. Hate when that happened. Let's see. Okay, now it worked. Now I can erase this one. Four different ways of changing the magnetic field that's inducing a current. The most practical way to induce a current is this last one here that I wrote down. That's the most practical way. That's the one that's used out there in the power plant that transmit electricity to our houses. Okay. And the direction of the magnetic field, whether the magnetic field decreases, or increases, Any questions about that? Let's see if we can see another way of inducing, using one circuit next to the other, right? Let's see if we have it here. Electromagnetic law. Well, I don't think we have it, but keep that in mind. Now let's talk about Lenz's law. Lenz's law. The direction of the induced current. That's what Lenz's law is all about. It's here you go. Well, it is a law. Let's keep it as a law for now. The direction of the induced current. Let's come up with an illustration here, okay? So stick to those 1, 2, 3, 4, right? So the direction of the induced current is going to depend on two things, right? One, the direction of the magnetic field, and two, whether the magnetic field is increasing or decreasing. In this specific case, I fixed the direction of the magnetic field into the board, okay? And how do you know? And now you have to tell me whether the magnetic field is increasing or decreasing, right? So let's use this one. Is the B field increasing or decreasing, right? That's that's what you have to ask yourself, right? There's a very simple rule, a very simple law, okay, that spell that, okay? The direction of the current is determined by, right? By the direction of the magnetic field and whether it is increasing or decreasing, okay? And how can we find out the exact, right? The exact way. Here you go. I'm gonna use this illustration here for you. We already know that, let's see here, I'm going to get this one. This one that we know that the current is flowing the clockwise direction, right? And by using the right-hand rule, we can say that the direction of the current is into the board using the right-hand rule, okay? Make sense? Current is flowing in the clockwise direction. I'm going to put this B as a function of time. And the Lenz's law states that the direction of the magnetic flux opposes the direction of the induced current, okay? Don't forget, this is the direction of the magnetic flux, okay? So here you go. According to Lenz's law, of the magnetic flux must oppose the direction of change. Let's see. Let me see if I can phrase that in a better way. The direction of the, according to Lenz's law, the direction of the induced current, right? Let's see. Okay, of the let's keep of the magnetic flux must oppose the direction of change of the induced current, and vice versa. Okay. So let's play a little bit with this here. Okay. Let's say the magnetic field is increasing, right? Let's say the magnetic field is increasing. If the magnetic field is increasing, the magnetic flux must increase as well, right? But according to Lenz's law, the direction of the magnetic field must oppose the direction of your current. So right from the bat, we see that the magnetic field cannot be increased, cannot increase, okay? But what if the magnetic field is decreasing, right? If the magnetic field is decreasing, the magnetic flux is also decreasing. Since it is decreasing, the current must flow in the same direction as the magnetic field, because according to induction law, it must oppose the change. Oppose the change, okay? So the situation is like that. Here you go. Example. If the magnetic field is into the bore, into the plane, right? Into the plane of the circuit, and it is increasing, comma, then the induced current must flow in the counterclockwise direction. Okay, it will oppose the direction of increase of the field flux. Okay, example. Let's put examples here. One, if the magnetic field is into the board, right? And it is increasing, then the induced current must flow in the counterclockwise direction. It must oppose the direction of increase of the field flux. We can come up with an illustration here, right? Let's see how I'm gonna do. I'm gonna do like that. Delta B over delta T. Let's see if you already have one. No, I don't have one. Okay, so I'll have to do that from scratch. Yeah, here you go. Delta B, let's say delta B symbol over delta T greater than 0. Greater than 0. Greater than 0. Delta B, delta T greater than 0. And now we go. Let's see here. Let me organize better this thing. Oh, I want to use this one, right? So here we go. Let me erase that for now, okay? Delta B, delta T greater than 0. So what happened here? According to Lenz's law, the flow of the current must oppose the change in the magnetic field. Consequently, here the vector of the current, right? That's what the thing means. The vector of the current must oppose the direction of the magnetic field. I have to change that. Let's see here. I'm going to do that. I'll have to do that from scratch. Field, right? And I'm going to change the color to distinguish one vector from the other. And what else? I have to show the direction of the electric current that must oppose the direction of the external magnetic field. Right in here, like that. Magnetic field increases with time. Okay. Consequently, the current must flow in the counterclockwise direction. Let me group that. I will copy and paste this one because I'm going to need that later on. I will counterclockwise direction. Oh, nope. Let's see here. I wanted this one only. Yeah. Right. Copy. Let's see here. counterclockwise direction is the other direction. Right? That's the direction of the induced current according to the right-hand rule. Magnetic field into the board, into the plane, right? Into the plane, increases with time. Current flows in the counterclockwise direction, like that. Now we're going to do for the other case, right? For the other case, here you go. Magnetic field is decreasing in time. Consequently, magnetic flux is decreasing in time as well. B field decreasing in time. Decreasing in time. B field. The B field actually is into the screen, and decreases in time. I'm going to do the same for the other one here. Here you go. Increases in time with time. Increases with time. Decreases with time. Okay, here you go. Decreases in time. So what's going to happen? The induced current must flow in a direction that opposes the change in the flux. By opposing the change in the flux, I mean that the direction of the flow of the current must be into the board, like that. Okay? That's what they mean by opposes the change, right? If it's into the board, then the direction of the induced current must be in the clockwise direction. This one right in here. And then you can repeat the same thing if the magnetic field is in the other direction, okay? That's 10:49, right? Any questions about that? That's the easiest way to visualize the induced current. Then there are other ways that there are other situations that are a little bit more complicated, okay? But for now, let's stick to this one so you can have an idea of how electromagnetic induction works. And let's take our break. Any questions? Break from 10:50 a.m. to 11:05 a.m. Any questions? Okay, so let's take our break now. And then when we come back, we do lab 3. Okay? So see you in 15 minutes. Oh, let's see. There's a question here, right? Oh, good morning. Okay, thanks. Stop sharing and stop record, pause. Okay, I'm back here. By the way, can you confirm that you can hear me?
I can hear you.
Okay, thank you. Okay, so let's start sharing the screen here. We are going to do lab 3 today. I'm going to upload the spreadsheets to your group folder. Let's see here. Okay. Okay. There is. Let's see. Let's see. Let me. I'm going to stop sharing momentarily. Remind me to share again, okay? Later on. Oh, man. Oh, gosh. Oh, okay. Now I am going to share the screen so I don't forget. Let's upload the spreadsheets. Google Drive. Physics 7, group 1. Oh gosh. Ay, 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 ay. Group 1 already have your spreadsheet there. Group 2, Group 3, Group 4, Group 5, Group 6, Group 7, Group 8, Group 9, Group 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so you have your spreadsheets. Okay, so you download the spreadsheet from your group folder in the Google Drive. Okay, so here you go. Admit. And to your hard drive, right? To your hard drive from the group folder in Google Drive. What we're going to do today, we will verify experimentally the relations we obtained in class for resistors in series. We will verify experimentally the relations for the equivalent resistance we obtain in class for resistors in series and parallel. It's possible everything that we taught there for those resistors connected in series and parallel can be verified experimentally. Let's take a look at the app slides, resistance measurement. Okay, this is the multimeter that I'm talking about, okay? Am I sharing the screen? Yeah, I'm sharing the screen. This is a fancy multimeter. You know, like I said, there are a bunch of multimeters out there. The one that I have is much more compact than this one that you see, okay? The one that we have, LA Hybrid, also is more compact than this one that you see here. They all do the same thing. They all do the same thing. But let's see, so far, so far, we have used the DMM digital multimeter just to measure the voltage. Today, we will use the DMM to measure resistance. Measure resistance using a series of resistors. If you go ahead and open your spreadsheet there in your let's see, lab. Actually, let me open this one here. No, not this one. I want the other one. I want this one here. Yeah, here you go. Okay, so here you go. Okay, when we perform this experiment, what do? I give my students a total of 6 resistors. Let me erase this one as well, erase this one as well. Oh, by the way, let me double check one thing here. Should have done that before for uploading actually. View. So 50%. Okay, good. 8. That's clean. 7. 6. 5. 4. 3. Just want to make sure that the spreadsheets are clean, doesn't have anything else other than what you're supposed to get there. Okay, 11. Let's see. Let's take a look at this one here. Oh, yeah, here you go. Group 18. Do you have group 18 there? Is anybody from group 18 here? Let's take a look here at my roster. Group 18. Juan Torellano. Juan Torres Arellano, sorry. Juan Torres Arellano is not here, right? Okay, and Chris Anthony, are you there? I don't see Chris. Okay, let me remove and move to trash. Trash. Okay, let's see if we have any other. And I need to upload a new uh, 318. Okay, good. Now this should be good. Sometimes I leave behind the stuff that I was not supposed to leave, right? So I forget. Now let's take a look at this one here. 17, that's good. 12, nothing. 16, 16, 15, 15. That's 14. 13. 11. Oh, 11. Okay, is group student of group 11 here?
Yeah, I'm here.
Okay, so delete that spreadsheet that I upload for you, please. I'm gonna upload another one.
Okay, thank you.
Okay. So let me. Group 11. So I'm gonna delete that, move to trash, and use this one here that I'm uploading right now. Okay. Group 11, who's that? Catherine, right? And Nadia. Let's see, who's Nadia? Yeah. Catherine
Yeah,
is
I
not here.
downloaded I
Okay.
downloaded the new one.
Okay, good. Your group member is not there with you, right?
I don't think so, not in class, no.
Catherine Michelle. Okay, good. So just use this spreadsheet, this new spreadsheet. Let's see here more. And okay, group 19. Okay, group 19. There's no group 19, so I don't have to worry about it. Good. So we're in good shape. You should have everything that you need. And let me walk you through the step-by-step procedure, as well as the equipment that's used in this lab. So far, we have used the DMM just to measure voltage, but the DMM can be used to measure other parameters as well. One of them is the resistance of, and what, and by the way, the DMM can measure other stuff too, other things, okay? Here you go, here's a list of parameters that the digital multimeter can measure. That's why it's called multimeter, right? Multimeter that measure multiple parameters. You can measure the voltage, you already know that. You can measure the resistance. When he's measured the resistance, we call it an ohmmeter. When you measure a voltage, we call it a voltmeter. And later on in other experiments, we are going to make measurements of the current as well. And when you measure the current, we call it an ammeter. But most multimeters measured those three parameters here, most multimeters. And then fancier one will be able also to measure the capacitance of a capacitor, the frequency of a circuit, okay, and even the electric field. The multimeters that measure the electric field directly, right, are the most expensive ones. Expensive ones. Okay, so let's talk about the list of equipment and materials. Okay, when I do perform this experiment, I distribute a total of 6 resistors of different values to my students. And let me show you how a resistor looks like. Those devices are mass manufactured nowadays. I believe I already showed that to you before, right? When I was doing the lecture, but I'm going to show to you again, just to as a reminder, resistors. Resistors, how they look like. No, they can be small devices or they can be large devices. And the ones that we use in the lab are small devices. They look just like that. Let's see, this bulb that you see right in here is usually 1 inch long, less than an inch long, okay? Has 2 leads. Just the bulb part, okay, is less than 1 inch, less than 2 centimeters, and has those leads that you see here to connect to your circuit. On the top of that, those resistors also has this color code that you see here. Bands, right? Bands with color. Here you have blue, green, orange, and brown. Here you have this thing here looks like a brown, right? Brown, red, brown, brown, white, brown, yellow, and looks like brown, this one, and so on. Those colors that you see in the device has a code, has a number code to it. Each color that you see here represents a number. Okay, each color that you see here represents a number. And those numbers are used to decode what is the value of the resistance of your resistor. So each of those resistors that you see here have a different resistance value. Okay, so 6 the resistors of different values. Okay, each resistor have a color code that can be used to determine its resistance value. And we used to do that in the old times, okay? The old times we need those color codes because at that time, multimeters, right? Ohmmeters that measure the resistance of the resistors were very expensive. Nowadays, you have those ohmmeters and multimeters that starts costing around $10, $10, $15. They're much cheaper. And we prefer to measure the resistance of the multimeter using we prefer to measure the resistance of the resistor using a multimeter. Okay, so what we are going to do today, we are going to compare the measurements obtained with the DMM with the color code in the resistors, okay? In this experiment, we will compare the values of the color code of the resistors with the resistance measurement using the digital multimeter. That's what we are going to do. So list of equipment, 6 resistors of different values, digital multimeter to measure the resistance, and a prototype board to connect our resistors in series and parallel. Let's take a look how a prototype board looks like. All those here are devices that are standard in every electronic laboratory. Only 3, right? 3 devices. Let's take a look I'm gonna show you the digital multimeters again, how they look like. Digital multimeter. Here you go, a bunch of digital multimeters. Let's see, instead of digital multimeter, just like multimeters, right? You're going to see analog multimeters as well. Before the digital multimeters came to the market, we had the analog multimeters. So those are all sorts of multimeters that you're going to see out there in the market. Oh, here's an analog multimeter. This one here. It has, just like that multimeter that you saw in the YouTube video, right? With a scale and a needle that points towards the measurement. This one has a scale in ohms, right in here. I scale in volts and ampere. Okay, and you have a more sensitive scale in ampere, microampere and milliampere, and an indicator of the battery. Okay, when the battery is discharged or whenever it's still good, bad and good, right? That's an analog multimeter. We don't use those analog multimeters anymore. Rarely we use them. We rarely use them. Okay, the pricing that you see right in here. Let's see, those pricings are in Brazilian reais. And 1960 reais is something more. This one is very cheap. I never seen this multimeter so inexpensive. You divide that by 5, it's $4 only. This multimeter that you see right in here. I have never seen a $4 multimeter in my life before. The cheapest one I have seen was $15. This one divided by 5, you get around $60. Okay, this one divided by 5, you get around $20 and so on. Okay, the price of the multimeter depends on what it does, how many significant figures it displays, depends on how many measurements it can also make, okay, and so on. And here is my multimeter with the big box, like the big box instead of that small device. After turn on the MM, default measurement is always volts. Okay, and then since you are going to measure resistance, we have to press this button. Either press this button, or if you're using the other multimeter that you saw, okay, like for instance, this one right here, you tune this thing here to measurement of the resistance, right? This indicator here, you gotta switch all the way down here to resistance, ohms. And that's what we're going to do is this device. Don't forget we have the jacks here. This multimeter, the jacks are in the right side, red jack and black jack. The other multimeters, the jacks are right in here. They didn't color code it. It's a problem, okay? I don't like this multimeter because they didn't color code it. Here's the negative terminal. Here's supposed to be the negative terminal. Let's see. Let's take a look at this one. This one they did color code it. That's good. They did color code. The negative is black. The positive is red. Okay, if you are using this multimeter to measure voltage and resistance, you use this red jack. If you are using the multimeter to measure current, you use this red jack. The black jack is common to both of them. They are both two different circuits inside this device, okay? So you can turn off this multimeter, measure voltage. This is AC voltage. Here is DC voltage. Here is AC and DC voltage, apparently. Yeah, ohms. Here is for diode measurement. We're not gonna cover that. This one we measured current and AC current and DC current. Okay, we haven't covered AC measurements yet, but we did cover DC measurements for voltage, and we are covering DC measurements for resistance. Okay? And we go, so what do? We get the black banana termination to black jack. Let me put here in the list of our equipment, right? Device, here goes 6 resistors of different values, digital multimeter to measure resistance. Red probe to use with the multimeter, to use with the DMM. Black probe to use with the DMM. To close the circuit, let's take a look how those probes look like. Multimeter probes. Multimeter probes. Okay, here you go. That's how they look like. Here is the termination, right? Black and red termination that goes in that jack of the multimeter. And here are the probes that will touch the terminals of the resistor. The tip here is a metal tip. It's supposed to be a metal tip that's covered by this plastic cover. Let's take a look at another. Okay, here you go, another one. This one is the most common one. Okay, here you go, here, black and red. That goes to the jack of the multimeter. And here the probe was the metal tip uncovered. Okay, so it's very easy to make resistance measurements. I would say the simplest way to make resistance measurements, the simplest way. Okay, insert red alligator clip to the other end of the red cable. Let's see here. Insert back to the other end of the black cable. What's that here? There's something wrong here. Okay, black banana to black jack. Okay, this one is correct. Red banana termination to red jack, black banana. But this one here doesn't make any sense. Let me take it out. I'm gonna put that at the bottom. Since we're making, oh yeah, we can put it. That's right, we can put it. We can leave it. Okay, why is that? What's the red alligator? The red alligator is a much more convenient way of grabbing that tip of the resistor. Let me see if we have, so what do? We adapt this probe here to the alligators, okay, to the alligator's clip. We attach the alligator clip to this tip. And now the alligator clip can bite the terminal of the resistor. It's a more convenient way of making a measurement, okay? Let's see if they have probes with alligator tips. Multimeter probe with alligator clips. Yeah, they do have it. Here you go. See that? And we'll have, see, that can also be used as a probe for the multimeter. See that? We have the one termination, which is the banana termination that's plugged there in the multimeter jack. And the other termination is the alligator clip. This one is a much more convenient way of making measurements of the resistance. Okay? The probe are better used to make a measurement that doesn't require too much stability. And let me put, here you go. Red probe to use the DMM with banana termination, and alligator with banana and alligator clip terminations, with banana and alligator clip terminations. And I'm going to put red and black probes and black probes. Okay. The banana termination is connected to the VMM jack, and the alligator termination to the lead of the resistors, like that. And then we have this prototype board. It's also a standard equipment in electronic laboratory. Let's take a look here at the prototype board. Prototype board. Yeah, that's how they look like. They have a bunch of holes right in here where you can build your circuit with different devices. And they have all sorts of sizes and shapes, okay? Can be large or small, just like that. And they are numbered to help you keep track of your connections. And the way it works, I want to show you how it works, the prototype board. Clamp alligator clip to the other end of the resistor, measure your resistance, right? So use the most sensitive. I tell my students to use the most sensitive scale in your DMM by pressing the arrow down. And here you go. Here is the prototype board. I didn't put all the holes in it, but we have holes here, you have holes in here, and we insert the resistor with their leads into those holes. Okay? That's how we do it. And when we want to connect those resistors in series, we connect one of their leads along the same row in this direction. All those holes that you see right in here, they are connected to each other in this direction, but not in this direction, okay? In this direction, they are not connected. It is as though as you have a metal wire along this row that you see right in here. So when you connect the resistor, one resistor in this spot and the other resistor in this other spot, it's as though as you have connect the two resistors in series, okay? Another way of connecting the resistor in series is just by touching one terminal. One of their terminals is the terminal of the other, just like you saw before. Let's take a look. Let's go back to our resistors. Yeah, here you go. Our resistors here, right? If you connect this terminal to this other terminal of the other resistor, this terminal of this resistor to the terminal of the other resistor, you are going to connect those two resistors in series, okay? And that's what we did in that drawing. In order to connect them in parallel, this terminal must be connected to this terminal, and this other terminal must be connected to the other terminal. Okay? Let's write it down. Okay? Here you go, in our notes. Okay, each should have a color code, value, and two metallic terminals, conducting terminals. Let's put it, conducting terminals. Okay. This is a convenient way. Although we can connect resistors in series and parallel, without the prototype board, right? Oftentimes, it is very convenient to use these boards. Okay. And let me give you the color code of those. The color code table for resistors. Okay, let's see, where is that? Oh, right in here. Each color, like I mentioned to you, signifies a number. Most resistors have 4 bands. Most resistors have 4 bands. Black color means 0. Brown, the number is 1. Red, 2, and so on. Okay. And we are going to make some examples. Let me get this sniffing tool. Here you go. So again, we are going to measure the resistance values of your resistor using 2 techniques, the color code and the multimeter. Okay, the color code is more awkward than the multimeter. I prefer to use the multimeter, but I want you to expose you on that because you may need that in the future. Okay, the color code was used in the past when the multimeters were very expensive, but nowadays, here you go, color code for resistors. And it is, right now, it is 11:50. Let's take our break. 11:50 a.m. to 12:05 p.m. Right? Any questions about that before we go? When we return, I'm going to show you how we use this color code. Okay? So I see you in 15 minutes. We're back here. Let me share the screen. Let's close it here. Okay, so here goes. Let's get some examples here on how we can use this color code chart. It's not difficult. Let me get, let's see, one example. Let's take a look. Okay, let's take a look at this one here. Copy. Pick up. Okay, so let's see. Let's get what's the resistance value of the very first resistor, right? What is the resistance value? Example. What's the resistance value of the very first resistor at the top of the illustration? Okay, solution. colors are blue, green, that's orange, right? And looks like a silver. The last one is silver. Colors, blue, green, orange, and silver. So when we have 4 bands, okay, the first 2 bands represent the digits of the first 2 significant digits of the resistance value, okay? Resistance value. So blue and green, let's go there to our color code here. Blue, here you go, blue, it represents 6. And green represents 5, okay? So here you go. We have half of the problem solved. Blue is equal to green, to 6. Green is equal to 5. So here you go. We start 6, 5. First 2 digits. Only 2 significant digits, okay? 65. Resistance is equal to 65 times something else. Something else that we are going to find out, okay? The third color represents the power, the exponent power of the resistor. Okay, resistor. So orange, let's go take a look. Orange, which orange it is number 3. Okay, because it is the third band. Look here at this column, right? It's a multiplier number. Number 3 means 10 to the third, or 1 kilo ohm. 10 to the third is 1,000 ohms, right? Or 1 kilo ohm. Got it? Okay. If the third band was the black, so the multiplicative value would be times 1, right? 10 to the 0. If the third band was 1, would be times 10, times 100, times 1,000, and so on. That's what the third band means. So in our case, what we end up having here is 65 times 10 to the third ohms. To the third ohm. And then we have the last band that I'm going to talk about. That's the value of the resistor. But we are not done yet. There is one more important. The fourth band is silver. And what does it represent? Let's take a look here. Silver represents the tolerance of the device, plus and minus 10%. Okay, the fourth band colored band represents the tolerance of the resistor. And what do we mean by tolerance? Okay, in the case of silver, the tolerance is plus and minus 10%. And what does it mean? It means that the resistance value can be anywhere between 65, but don't forget, we have only 2 digits here, 2 significant digits, okay? 65 times 1,000, 65 kilo ohms, let's put it this way. 65 kilo ohms. The value of this resistor, right, is anywhere between 65 kilo ohms minus 6.5 kilo ohms, anywhere between this value and 65, let me put here you go this way, kilo ohms plus 6.5. That's the tolerance value that we are talking about. It's anywhere between this value. The resistance value of this resistor is anywhere between 65 kilo ohms minus and 65 plus. And then you do the math, right? Got the idea? There are resistors. There are resistors that also have 5 colored bands, okay? In this case, the first 3 digits are the 3 significant digits of the resistor, and the other 2, the first 3 colors, right? The first 3 colors are the 3 significant digits of the resistor, and the other 2 are the multiplying factor and the tolerance, respectively. So it's very simple once you memorize this rule. It's very simple to find out the resistance value of your resistor. Okay, so here you go. I provide, that's the step-by-step instruction of the experiment, provide the students with 6 different resistors. The student used 2 different methods to determine the resistance of each individual resistor, using the color code and using the DMM. One, to measure the individual resistance of each resistor, to measure the resistance of the 2 resistors in series, to measure the resistance of the 2 resistors connected in parallel. It's far more practical and quicker to determine the resistance of the resistors using the DMM, okay? So spreadsheets, let's see here. They're not due today, right? No, erase that. Oh, doesn't apply to you. Here is the instructions, right? That I just went through. It's just a repetition of what I did. Here you go, another example. Yellow, violet, orange, and silver. Okay. And now let's take a look at the tables in the spreadsheet. Here you go. The nominal, here you go, the first table have the nominal value of the resistor. The nominal value means what? The color code. Nominal value means color code, okay? R sub n. And I already provide you with the numerical value of those resistors. And let's not forget, the nominal value must have two significant figures only. Okay, so nominal value means color code value of the resistors. All resistors of the lab have only 4 color codes. Consequently, right? Consequently, the number of significant digits of the nominal values should be only 2. Okay, should be only 2. And so this one is 180, right? This other one is 120, this one 56, and so on. So you have to display those values with the proper number of significant figures. The lower value is the nominal value minus the percentage, the tolerance, and the upper value is nominal value plus the tolerance. In this column, we have the measurements with the multimeter, E&M measurement. And the number of significant figures should be determined from that table that you downloaded from the Canvas course site. The first thing that you're going to do, let's do what is important, right? Do the following. Plot the nominal value along the x-axis and the E&M value along. There will be a total of 3 graphs. Let's make sure it's 3 graphs here. This, okay, you're going to plot this graph here, nominal value and measured value. The slope of the curves are going to be very close to 1. That's one graph. You are going to plot this one here. Okay, those are the resistors in series. So all I did was to sum R1 is R2, R1 is R3, and so on, right? You're going to plot this one. And then you are going to plot this one right here. 1 over R, E&M, against 1 over R1 plus 1 over Rj, okay? Which are the resistors in parallel. Let's start with that, right? Here you go. I'll plot here one of them, E&M, nominal value, insert, chart, boom. Note, see, that's a very linear relationship, right? Which shows that the measurement of the E&M and the nominal value has a linear relationship. Now let's take a look at the trend line. Display R squared, display equation on chart. So like I said, the slope, look here, is very close to 1. What does it mean? It means that the resistance measured by the multimeter and the resistance of the color codes, they're very close to each other. There is a small intercept value here. Then you can do the other things, right? Next, the next graph is going to be the resistor in series. Here is an actual measurement with the multimeter. The actual measurement with the multimeter is made with those resistors connected in series here using the protoboard, the prototype board. So what did I do? We connected the R1 in series with R2, the R1 in series with R3, and so on, right? When we plot those, in the first graph, you have 6 data points, right? 1, 2, 3, 4, 5, 6. But in the second graph, I want to warn you, you have only 5 data points. 5 data points because I'm combining the first resistor with 2, the first resistor is 3, and so on. So insert, if I did everything right, you should get a straight line. Click it here, right? Trend line, yeah, and then what do we get? Yeah, you will get a slope that's very close to 1, which shows that the measurement of the multimeter is very close to the measurement provided by the nominal values. And then we plot the third graph. But remember, you're not plotting this column here. I want to warn you, folks. You're going to plot the inverse, right? Measurement of the inverse of the measurement. Here's a measurement. Here's the inverse of a measurement. Here's a raw data. Here's a result of the raw data. Here's the same thing. Here's a result. Here's another result, right? And you're going to plot again. You're going to plot this one here, 1 over R DMM, 1 over R1 plus 1 over R, RJ. So those numbers should be very close to each other. Oh, here you go. They're linear. Definitely they're linear. Let's see if the slope is very close to 1 as well. Display equation chart. Yeah, only 1% difference, right? 1.01 represents only 1% difference. And look at this value. Here, R squared is not 1, right? R squared is slightly less than 1. So when you see something like that, R squared equal to 1, you have to increase the number of decimal places here to get the actual value. Let's take a look here. Select data, format trend line label. That's what you want, format trend line label. Where's that? Okay, number. Number. You want a number, and then you want to increase the decimal points until you see a number that's not 1. 5, okay, 5 decimal places. See, it's 0.99999. 3 graphs. What time is that? 12:27. We still have almost half an hour to go, right? 25 minutes to go. That's what you have to do. Resistors in series and 3 resistors in parallel. Okay. After that, table 4-2. What's table 4-2? What you have to do in table 4-2? Table 4-2, you have to fill up this table, right? That's for the CL. Number of data points in your graph, the regression equation, and the R squared. And then you fill up what's the upper and lower values of the CL. Upper and lower ranges of your actual CL. Next, table 4-5. Let's see what's table 4-5. Table 4-5. Okay, let's see. Slopes. You got to write down the slope values according to the equation, to the regression equation that you got. And this, what you're going to get here are the percentage differences with respect to the expected value that was going to be 1, okay? That's what you have to do. So let's, and then what else? Fill up the units, the measurement units, right? The measurement units, something that you have been doing. Here you go. I put the unit here, then you have to fill up here, here, here. And here too, right? Yo. What's going on here? Yep. Units here, unit here, unit here, unit here, right? unit, there's no units here in this for second table, but then you must write down the units here, here, and here. 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 Which other units do we need to write? Oh, right in here. Don't forget, people, I'm not asking you to write down the units of the resistance, but the inverse of the resistance, okay? Inverse of the resistance here, unit of the inverse of the resistance here, unit of the inverse of the resistance here. The exception is this one. I want the unit of the resistance here, and then the unit of the inverse of the resistance here, plus the unit of the percentage difference, the unit of the slope, the unit of the percentage difference. Okay. Next, display the proper number of significant figures using the document provided. And finish table 4-2 for export cell, right? The table provided is in Canvas. Let's go back there. Confidence level, here you go, physics lab. P07 significant figures. Download it. I downloaded it. Here you go. Here. Here's the table. No, not this one. It's this one here. Let me move away. Let me zoom in. That's the table for resistance of the DMM for the specific multimeter that we use there in the classroom. Okay. If your resistance is between 1 and 9.99, you have to display 3 significant figures, right? If the resistance between 10 and 99.99 is 4, and so on. Let's do one example. One example, here we go. This resistance value right here is 180, but that's for the nominal value. If it is for the nominal value, you have to display this value with 2 significant digits only. And in order to do that, you cannot display it as a numerical value, right? Remember that rule? You cannot display it as numerical value, because if you display as numerical value, you'll be displaying 3 significant figures here. So in this specific case, you have to use that technique using the scientific notation. When you use the scientific notation, you can display only 2 significant digits. So how do you do that? Right click, format cell, scientific notation. Right now, we have only 1 significant digit, but if we increase the number of decimal places to 1, now you have 2 significant digits. 2 significant digits in scientific notation. Sometimes you must use scientific notation to display the right number of significant digits of your measurement, right? But that's for the nominal value. For the multimeter, we have to use the table that you saw. Here you go. The value is 177.5. Let's take a look. 177.5 falls right in here. Okay? So this value must have 5 significant digits. 5 significant digits according to this table. So let's see how we are going to do, right? I'm going to, this one we can display in numeric format. And I'm going to display with numeric format with 0 decimal places, right? If I display with 0 decimal places, I get only 3 significant digits. Remember that we have to display it with 5 significant digits according to the table. 5 significant digits. So what we have to do? We have to add 2 more decimal places. 1, 2. Okay? And you gotta do the same for the rest. It's 12:34, 15 more minutes to go. Any questions? Okay, and so let's see how you are doing. I need you to plot the graphs. Today is the 1st of April. Let me go one by one so you can participate. Download, did you download? Mirage is here. No, Mirage is not here. Next one in line is Susan. Susan Acosta, are you there, Susan? I don't see Susan. Next is Mikara. I don't see Mikara either. Ryan. I don't see Ryan. Evelyn Ayala. No, Evelyn. Christina. No, Christina. Ben Bandoy. Ben Bandoy is here, right, Ben? Okay. Okay, did you download your spreadsheet, Ben? That's the first question that I'm making. Yes, and I already plotted them. Oh, all the 3 graphs? Okay. Oh, good. 3 graphs. 3 graphs, plotted them. Good. So next in line should be the units. Okay. Did you fill up the units already? No? Okay. So start working on that. Okay. The units should be either the ohm or the percentage difference or the inverse of the ohm, right? Those are the 3 possible units. Okay, so I'm giving you the, ohm. Here is going to be the percentage, which is a unit. Here is going to be ohm as well, right? Percentage. Here is going to be the inverse of the ohm. Only 3 different units that you have to. Oh, that we do also have the slope, the unit of the slope, right? So 4 possible units. 4 possible units. Now, next in line here should be Queen. Are you there, Queen?
Hello. Yes.
Okay, hi. And did you download your spreadsheet?
Yes.
Okay. Did you plot your 3 graphs?
Yes.
Okay. What about the units? Did you work on the units
No.
already?
Working
No?
on units.
Okay. Working on the units right now. If just a little trick here that you gotta know, right? If you do not know how to write ohm, all you have to do is to copy this one and paste elsewhere, right? That's all you have to do. Now, if you want to know exactly how to write down the ohm, how do we do it? The ohm is the last letter of the Greek alphabet. Okay? And the last letter of the Greek alphabet is not zeta, no. Zeta for Z, right? It's not. It's omega. Omega is W in the Latin alphabet. So if you write W here and then you change the font of W, font, where is font here? I don't see font here. Okay, so font is here. That's another place that you can look for font, right? You change the font type from Calibri to symbol, okay? And then if you do that, the W becomes omega. And if you want to, that's something that you end up memorizing after working hard, right? If you want to play a little bit with that, right? Just to type every letter in your keyboard, like A. A is alpha, right? B is beta. That's the lowercase. C is gamma. No, C is chi. That's chi. D is delta. E is epsilon. A, B, C, D, E, F. F is what? Phi. F is phi. G is gamma. Gamma is G. A, B, C, D, E, F, G, H. H is eta. Eventually, you memorize the Greek alphabet, the letters of the Greek alphabet. Let's see. A is iota, right? The Greek letter, the I, the respective I in Greek, right? I, A, B, C, D, F, G, H, I, J. J is this one I believe is, I think this one is phi as well. I don't remember that, but that's okay. K is kappa, very similar to the K in the Latin alphabet. K, L is lambda. The JKL, M is mu, N is new, right? M N O is omicron. MNAOP is pi is P. That you cannot forget, right? PQ is gonna be theta. R is rho, R is rho, S is sigma, right? So play a little bit with that so you can, let's finish, right? T is tau, U is, I don't know the name of this letter. U, V is, I don't know the name of this letter either. V to V, X. Yeah, I don't know the name of this one either. X. I memorize only a few, most of them, right? X, Y. Y is psi, right? Psi, the symbol for psychology. Y, yeah, Y. W, W is omega. Lowercase, those are all lowercase. Z. And Z, I do not know the name of this letter, but I know most of them. Okay. And then if you want to do uppercase, right, you do uppercase as well. They are slightly different. It is very handy to memorize A, B, C, D, E, F, G, H. Oops. I think G, H. Okay. I, J, K, L, M, N, O, P, Q, theta, R, S, S. This is called sigma. This one is called sigma, this formation sign. T, U, V, oops, W, X, Y, Z. Okay? Those are the corresponding capital letters in the Greek alphabet. Okay, all you have to do is to change the font to symbol. They display here in Latin alphabet, right? And here is displayed as a Greek alphabet. Okay, one student coming in. Let's see. We have 7 more minutes to go. Who's next? Emily. Emily, are you there? I don't see Emily. Isabella Cisnero. I don't see Isabella. Luis Cruz. I don't see Luis here. Delisha.
Yeah, I'm here.
Okay, just joined us. Okay, Delisha, we are doing the lab number 3. Okay, did you download the spreadsheet for lab number 3?
Yeah, I have it.
Okay, did you plot all the 3 graphs?
No, not yet. I'm gonna do that later.
Okay, start working on that. So, Gabriela Edwards. I don't see Gabriela here. Princess. Princess must be here, right?
Here.
Okay, did you download the spreadsheet, Princess?
Yeah, I did download it.
Okay, did you plot the 3 graphs?
Yeah.
Okay, all the 3, that's good. What about the units? Did you work on the units already?
No, I am working on that right now.
Okay, so let's go for Carlo Gallardo. Don't see Carlo is here, right? Yeah, good. Carlo is here. Did you download the spreadsheet, Carlo? Yes. Did you plot out the 3 graphs? Yes. What about the units? No. Okay, so work there on the units. We have 5 more minutes to go. Trin, are you there, Trin? I don't see Trin. Next is Stefan. Is Stefan there? I don't see Stefan. Jeremy. Jeremy, I don't see Jeremy. Paola Leones. I don't see Paola. Must be the spring break, right? Next week. Very few students today. We have what? How many? 11. Janie. Janie, I don't see Janie. Let's see. Wait a minute. Pedro, right? I don't see Pedro, Paola, Pedro. Next is Janie. Janie, I don't see Janie. Noemi. I don't see Noemi. Isabel Medina. I don't see Isabel. Kimberly Morales. Okay, see Kimberly. Are you there, Kimberly?
Yes.
Okay, did you download the spreadsheet?
Yes.
Okay, did you plot out the 3 graphs?
Yes.
Okay, do you work on the units?
I'm working that right now. Is
Uh,
it possible that you can show again uh the DMM again?
the let's see, let's go back to the spreadsheet, right? You want me to show what? The Greek alphabet?
No, the DMM.
Oh, the
The how
DMM,
how the
right in
yeah.
here.
Yeah, how does display the units for that one again? I was having
Oh,
difficult.
the unit is the omega, right? Is the ohm. You might be asking the significant digits, right? Is that what you're asking? The significant digits?
Yes.
Okay, the significant digits, right? So go back to that table that I provided to you in Canvas, right? P07 sig fig. Is this right in here? Let's go. Modules. Okay. See here. Physics lab. P07 sig fig, right? And here's the confidence level table. So that's the one you should be using for the significant digits or significant figures. And when you download, right, I download to my computer, I have it right here. You want, for this lab, you want to use this very first table because that's the one that deals with the significant figures of the resistance of the multimeter. Okay, so you go to your spreadsheet, you read what is the numeric value of your resistance is 177.5, and the number of significant digits is given depends on the range of your value. 177.5 is in this range here between 100 and 200. And the third column tells you that you have 5 significant digits. If you are using the multimeter that we use there at LA Harbor, you would see that you have 5 significant digits there. Now that you know that you have 5 significant digits, right? Let's put it back in when we had the scientific format. That was originally what you have, scientific format with 0 decimal places, right? So here you go. We have so 5 significant digits, right? So you gotta start, when we first start with putting in the numeric format, right? And then you count the number of significant digits. You have only 3 in this case. You want 5, you have to add 2 decimal places. 1, 2. for this specific numeric result. Okay? And now I have 5 significant digits. Okay, regarding the equation, right? The equation, are you talking about the regression equation, Ben? You're talking about the regression equation, right? Okay, yeah, you don't need to put all the five numbers there, but you will need to type the R square with that exact number of figures that you have there, okay? Don't type 1. Don't type 1 there. Type exactly the number of figures that you have in there. Is that clear now? Let's see, who am I talking to? Let me get back to your name. I was talking to Kimberly, right? Is that clear now, Kimberly?
Yes, it makes clear, but it's just my values are much larger than yours.
Okay. Oh, yeah, that's right. Because you have a different spreadsheet, right? That's why you have a different spreadsheet. So let's see. Let's get what group number are you?
6.
6, right? So let's go get your spreadsheet. But this whole thing that I told you can be extended. Here you go. For the DMM, right? No, not this one. This one here. DMM. Yeah, it's much larger. It's 14,000, right? 14,800. So you go here in this 14,800 is this row right here. See that? You have to display 5 significant figures. So you have to follow the let's say the instructions can be extended to other values, right? Make sense?
Yes.
If it is between 100 and 200, it's 5 significant figures. But if it is 10,000, between 10,000 to 20,000, it's also 5 significant figures. But if it is 2,000 and 9,999, it's going to be 4 significant figures, and so on. And then you have to play with the formatting and the number of decimal places there to get the right number of significant figures in your Excel spreadsheet. Okay? Can you do that now?
Yes, thank you.
And okay, it's we're 2 minutes past the time, 12:52. I have office hours right now. If you want to hang around to to ask more questions, just stay around and I'll help you out. Okay. Otherwise, see you 2 weeks from now because we're gonna have a spring break. Okay. See you then. Bye bye.
Thank you, Professor.
See you.
Thank you.
Welcome.
Thank you, Professor.
See you.
I have a quick